Thank you everyone for coming. My name is Greg Chase. I do community marketing for Pivotal during my day job. As part of my evening fun, I am one of the co-organizers of the Data Engineers Guild. And I'd like to introduce our first speakers, Esther and Srivatsan.
My name is Watson. I'm a principal data scientist with Pivotal. We are a team of 35 data scientists, and we've been fortunate enough to get to work on a lot of problems in the IoT space, particularly with connected vehicles. So the first 30 minutes today is going to be about the data science behind predictive maintenance in connected vehicles. So here we'll be focusing more on what is the data science methodology, what are some of the interesting problems that we face in the connected vehicle space, and how we solve for them. In the next 30 minutes, I also have my colleague Frank, who heads product management for some of our machine learning toolkits. He'll be able to walk you through some of the more intricate details of the product suite we have for building these data science models. And my colleague here, Esther Vastete, will walk you through in detail about the connected vehicle use case itself. Now, I don't have to tell you that devices are increasingly more connected. IoT is everywhere. It is not something which is spoken about only in some fancy conferences, right? So IoT and connected devices are in multiple verticals, right? So you have connected healthcare, you have connected devices in the vehicle space, like autonomous vehicles and what have you. You have connected homes, right? Now, what are some interesting applications of these connected vehicles? That's not the most interesting application, but think of connected home, right? How can these connected devices understand what is your preference for the temperature in your home? When to turn on the AC, figuring out when do you show up for home from work every day, and regulating the temperature accordingly. That's an interesting application. And then there are connected devices in the healthcare space, right? How can you take signals such as your EEG or your ECG and identify interesting patterns in these signals? How can you then build a smart application which consumes these models and alert the user? How can you ultimately give value to the user, which is what ultimately matters, right? There are examples of connected devices and its applications in the power transmission domain, right? So how can you identify a fallen power line even before the consumers report this issue? These are some problems we've solved for our customers, and they all pose interesting challenges, from the kind of data we collect to the kind of models you build, and how do you ultimately communicate these insights to your customers. Think about the Deepwater Horizon incident, right? What if you were better able to predict this disaster in the drill rig, which eventually led to a whole lot of damage to the environment? And how can data science help? So the applications are many, right? Now, what about data? The data in the connected devices are in various shapes and sizes, right? The bottom line is that there's a whole lot of data and they come in different textures. So you have mobile sensors, you have video data, you have images, you have humans interacting on social media. So there's a lot of text, right? So ultimately, you need the right set of tools along with the right questions to ask before you can use data science to build a solution to solve a problem, right? So realizing this opportunity requires the right tools to start with. So if you think about the different steps involved in going through this process, you first have to define the right problem. So this means asking the right question, determining what will have maximal impact to the users who are ultimately going to consume the data from these devices, right? So then you go on to understanding what data sources you have access to. Traditionally, most people have worked with structured data because of some of the limitations of the toolkits that they had. But you have platforms today and tools which can deal with data of different textures, shape, what have you, right? So these could be in the form of sensor data, as we discussed. It could be from social media information, it could be in textual form, what have you. So data comes in different flavors. Now, what about the modeling steps? Here's where once you've defined the problem, you've gathered your data, you apply all your fancy machine learning algorithms and your fancy machine learning toolkits to build something interesting. So there are several tools in this space, right? Most of you might have seen a bunch of these. There are machine learning toolkits for building models. And then there are, of course, exploratory data analysis toolkits. There's a lot in the Python space, and there's a lot in the R camp as well. Now, once you've built some model to answer the problem that you posed, you also have to think about how will you communicate these insights to your end user. As one of our colleagues put it, PowerPoint decks are where models go to die. So you want to think about what is the right way for your models to communicate insights to your end user. And there are several tools, again, in that space as well. You have tools for web frameworks if you want to build some application. You have a lot of fancy visualization libraries like D3. And you also have platforms on which you can deploy the application that you've built. So given that you have identified the problem, you know all your data sources, you have all these modeling toolkits at your disposal, and you have all these toolkits for building intelligent applications, what should you do? Should you just dive in? Thankfully, we have some words of wisdom from the great sage Big Data Borat. So if you do that, you would do development, you'll deploy, and ultimately you'll be setting yourself up for disappointment. Instead, what you should think about is what platforms do you have which can neatly glue these individual components together? And that's why you're all here, right? This is the Data Engineers Guild meetup. So you want to know about what platforms are out there and how do you integrate these components together. So let's take the connected vehicles example, right? So you have data coming in from your vehicles. You need some sort of an ingestion platform. So this is a key component of your overall solution. So this ingestion platform should be able to deal with high throughput coming in from multitude of vehicles. You need to be able to do some sort of intelligent processing. You want to collect data from other sources, right? So besides vehicle sensors, you have information about vehicle family and its GPS coordinates, what have you, right? And ultimately, you want to land it in a data lake. Now, this data lake could be anything. It could be an enterprise data warehouse. It could be Hadoop. But the bottom line is you want some place where you can store a lot of historical data before you can start doing data science. Now, once you have a data lake where you've stored all this data, you start doing some sort of exploratory data analysis using some of the toolkits we already saw. Now, that process should be quick. It should be able to scale to really large number of records, right? So the platform component becomes important. The modeling component becomes important. Now, once you've built some models, again, as I mentioned, you want to deploy some application which consumes this model. And this application is not something static. You want to improve your models over time. So there is this continuous feedback loop where the model is fed into an application that's consumed by some end user of yours. And based on their inputs, you retrain the model, you identify new data sources, perhaps you build a different model, what have you. And that is why choosing the right platform could make a big difference in this whole process and ultimately benefit your end user. Now, speaking of connected cars, what are some interesting data science use cases in this space, right? As I mentioned before, we've been pretty fortunate enough to have worked with a lot of clients from the connected vehicle space as far as data science problems are concerned. So one of the frequently occurring themes is predictive maintenance, right? So as I mentioned before, this is not a problem just restricted to connected vehicles alone. It is for IoT in general. So predictive maintenance, which will be the emphasis of the next 20 minutes of this session, is essentially identifying problematic things associated with your vehicle before they happen and cost you money. Perhaps you lose time when your car is in the shop if you haven't diagnosed this problem early enough. There's also a lot of use cases that we encounter in the space of understanding driver behavior, right? So this is of interest to insurance companies. We've worked with customers in Europe who wanted to understand by looking at a distribution of traffic velocities at different road segments, they want to understand, what components can explain a certain distribution of traffic velocities and why do those patterns exist. And they wanted to know this so that they could, use that in more intelligent navigation system, which brings us to improved GPS navigation, right? So understanding traffic congestion patterns, which I'm sure our friend from Uber will have a lot to talk about, could help you in better routing, right? Better route planning. You could also think about problems in the predictive power for assistance systems. There are vehicles which can automatically shut themselves off when you're waiting at a traffic light. Understanding where you're going to be in the next couple of minutes could help it in better managing fuel efficiency, right? That's another class of problems we've encountered. And finally, if you can predict traffic congestion, if you can predict where your vehicle is going to be in the next couple of minutes, and if you have improved GPS systems, you could even figure out how do you ride the green light, right? That could lead to better experience for the people who are commuting in that vehicle. Now, as I mentioned, the next 20 minutes, we are going to focus on the first of these use cases because that is what we see increasingly, and it has a huge impact for auto manufacturers, to automobile dealers, and as well as you, the end user who buys and drives this car. So I'm going to leave this to Esther, who's going to talk more about a certain use case we solve for one of our customers.
Yeah, so as he mentioned, I'm going to be talking about this engagement that we did with one of the major automobile companies. And we work together to build a data science model that would try to solve the preventive maintenance problem. So let me start by introducing the term diagnostic trouble code, or DTC codes, as I'm going to be referring to. These are codes that are transmitted from an onboard diagnosis system that comes in the car. And these are alphanumeric codes, such as the one here. Let's look at this particular one where we have a code P0302. So what that means is that we have a code subsystem P that refers to powertrain, and then we also have a C. What happened? Okay. So zero goes for a standardized code. So this means it's a. Should I go there? I'm gonna be coming here then. So yeah, so 0 goes for the type of code, whether it's a standardized or manufacturer specific. 3, then the next character refers to the subsystem. In this case, we're talking about the ignition system. And then the last 2 digits refer to a specific code or the exact problem. And in this case, 02 indicates for misfire detected in the second cylinder. And even though this seems like a very specific code, going from this particular code on your onboard diagnostic system in the car to an actual repair is the connection is not very clear. And there are actually many of these codes that are not really showing any symptoms on a particular repair that could be needed in the car. And so it has been very hard to be able to come up with kind of way to match the two. So this is how we could solve the problem instead of looking into like an if-else kind of a statement, like if this code appears in the car, maybe we need this kind of repair. Instead of like looking at the problem in that way, we could look at it using machine learning and using a lot of historical data to be able to match all these DTC codes with actual repairs. So let me clarify that I'm talking about repairs that are unscheduled. And also, let me clarify that the mechanics in the dealerships also use some kind of code for each particular repair that they do. And so automakers are able to get this data from their dealership network. So solving the preventive maintenance problem benefits multiple parties. On one hand, automakers can be able to monitor trending problems that they may have in their cars and potentially prevent recalls. They could also be able to identify possible parts in a car that may be faulty by looking at the causation between these DTC codes and the repairs. On the other hand, mechanics in the dealerships, they also may get some benefits from this by using some kind of repair recommendation system that may help them diagnose what the problem is with the car in an easier and quicker way. And so by doing this, it is our hope that the customer experience will also improve. So it's a really win-win-win situation here. So there are two major data sources that we work with in this problem. So on one hand, we have data that comes from the vehicle. So this is the sensor data. I've been talking about these DTC codes. So those are actual sensors that fire up once a particular sensor goes above some threshold that it's above a normal range. So whenever that happens, we also get readings about the mileage, what was the speed, the acceleration, the engine temperature, the GPS coordinates, and so on. So on one hand, we have all this data that is being streamed from a vehicle. On the other hand, we have data that comes from the dealer networks. And so these are car repair data. This data includes things like the vehicle identification number, so then we can match it to the other sources, but also when did this vehicle get into the dealership, when did it get out, what was the repair that was done, whether there were some parts that were replaced, were those parts under warranty, and things like that. So fortunately, most automakers are really good at getting the data from their dealer networks. And so it is crucial to have good car repair data to be able to solve this problem. So this is how a simplified version of the problem looks like. So we have a car out there, and one particular day, some sensor goes above some threshold, and so it transmits some DTC code, in this case B. And then maybe a month later, some other sensors also fire up, and then we see B again, because the DTC code can happen more than once, but also we see P and C. And then maybe a couple, 2 weeks later, another DTC code is transmitted. And so we kind of, we don't see anything else for the next couple months, but then one day the owner of this car takes the vehicle into a dealer, and it turns out this car, the mechanic did a transmission-related repair. So the question that we wanted to answer is, could have we predicted that this car needed a transmission repair based on what we saw here? And if so, how long before the repair can we do that? And so what I want you to focus on here, though, is how we have coupled these two different data sources into one supervised classification framework. And so in machine learning, a supervised classification problem is the task of being able to infer a particular function based on training examples. So here, the way we define the problem, our training examples is some sort of window of time where we aggregate all these sensor data. And so all these sensor data are these codes, but also, as I mentioned earlier, things like the mileage, speed, and things like that. So all the sensor data gets aggregated, and then on the other hand, we can label that training example with the repair that was performed. Okay. So as this is actually a supervised classification problem, as I mentioned. We have training examples. We have tons of historical data, and because we have tons of historical data, we can build a machine learning framework that could learn the relationships between the DDC codes and the particular repair codes. However, this is actually rather challenging because in our data set, we had about 40,000 different repair codes. And some of these repair codes are really, really specific. Some of these repair codes are really similar to each other, but a major problem was that for some of these repair codes, we didn't have enough data samples because some repairs may be rare and we didn't have enough data. So being able to identify from a set of vehicle features which was the very particular kind of repair needed was a challenge. But if we look at the hierarchical nature of these repair codes, we could identify that actually all these bunch of codes were related to wheel kind of problems, or how a lot of other repair jobs were related to engine related problems, or the same with the steering, transmission, and so on. So we can make our problem a lot more manageable if we first try to decide in a higher level what was the major problem that your car may need to be repaired on. So that's how we build a hierarchical classification framework. So on the first stage, we score our model and we try to decide, does this vehicle need any kind of repair? And if so, we, for instance, predict that we need a particular type of problem to be solved, then we can go down another stage in the hierarchical classification to a second stage and see what was the particular repair code that was needed. And so in this case, our model predicts that this vehicle needs a wheel kind of repair. And so once we get into that need, we can run a second model and say, okay, so if we need a vehicle, a wheel kind of repair, what is the exact kind of repair needed? And so in that case, we can go match the particular repair. And by doing this, why is it easier to do it this way? It's easier because if we are able to identify that a wheel-related problem was needed, and we correctly classify this, then we can get our data into a model that is specialized in wheels. And so by doing this model has been learning from wheel problems only. And so it is our hope that it would be easier to be able to identify the particular problem. And even if we don't get the second stage correctly, I think there is also a lot of value to be able to identify the first level of problem. So being able to say, hey, your car may need some sort of wheel repair, it's still valuable. So this hierarchical classification framework allow us to also divide the problem into different levels of difficulty. And also, let me remind you that this is not only a multi-class classification problem, but because on a given date, there could be more than one major problem that a particular car needs to be repaired on. This is also a multi-label classification problem. So there could be, at the same time, more than one repair needed. And because of that, because we have a multi-label problem as well, that leads us to follow a one versus rest classification strategy. In this case, what one versus rest strategy means is that we're not just building one model, one single model that is gonna identify whether a particular car needs a wheel kind of problem versus a transmission kind of repair versus a steering kind of repair, but instead we specifically build a different model per each major system. So in the case of a wheel-related repair, we build one model that it's gonna be able to identify, is this a wheel kind of problem or is it not? Is it any of the other problems? And because of this model parallelism, we were able to build all these models in parallel on a massively parallel processing database like GreenClam or Hawk by distributing the data across nodes. However, I'm going to let Frank talk more about that model parallelism. And so the key takeaways of this is that predictive maintenance is a challenging problem because DDC codes and repairs are actually not a clear connection between them. And so machine learning approach may be able to identify those patterns. Because of the many different repairs that you could do on a vehicle, we decided to build a hierarchical framework so that we could have the problem be more manageable and so that the problem that way is more manageable. And unfortunately, I cannot talk a lot about the insights and the results of those models, since I cannot also talk about our customer. But one thing that was very interesting is that the major systems, so whether a car needed a transmission problem or a steering problem, so those major systems, we could identify those very early in time, so very early before that repair date. So that allows for a lot of room for automakers to make some sort of action, to take some sort of action. And hopefully this will lead to safer automobiles. And so I'm gonna...
Thanks, Esther. So, all right, so we spoke about the platform enabling this sort of data science, right? Yeah, was that a question?
Can you repeat the question? Because yeah, but I also didn't get it. Yes, actually, can I talk about the details?
So the question, just to repeat the
Oh
question.
yeah, sorry.
So the question was, is the time between repairs also a feature in the model?
So not exactly the time between repairs, but some of the features were: is this the first repair? Was there some repair previously? Was there some repair of a transmission kind of model previously in this vehicle? So yes, we use all the historical data in the car, such as previous repairs and how long previously to those repairs. Those were features as well. Yes. Yeah, one question at a time. So first question. Sorry, not understanding.
Question. So the question is, how did you capture these DTC codes? Was it from the CAN bus? And the second question was, can you say that again? Whether it's common across OEMs. And the answer to the first question is, in this case, our customer already had the mechanism to capture these DTC codes from the CAN bus, decode it, and transmit it over a device and store it on a data lake. The data scientists then come and build models on that data, right? So DTC codes are pretty much a standard across, most automobiles to our knowledge. So yes, I think the DTC codes itself are not specific to a certain automaker. So that's why this particular analysis is applicable for other automakers as well. Great question. So the question is, did you have any mechanism to do some analysis on the device or on the vehicle before you send things out to the cloud? And the answer is absolutely. As the auto industry matures, some of these models will be applied locally on the device to correct some signal error from multiple sensors, right? These are just sensors, and sensors by their nature are pretty noisy. So you can push down some of that smarts to the device, and for more computationally intensive batch processing, you would build these models offline on the cloud. So we are running out of, yeah. Yeah. So we will still have time because Frank is going to be talking about the different components. So you'll have time at the end of the hour to ask more questions. Yeah, so the question was, who owns the data, and how do you handle that scenario where the manufacturers own some data and the dealers own some? So for vehicles under warranty, the dealers are required to share repair information to the automakers themselves. So the automakers gather this information. So they get sensor data from vehicles which have sensors in them, so they have that. But things like what repair was performed, what job was performed by a dealer is something that the dealers are required to share for vehicles under warranty. And in other scenarios, they could even sell it to the automakers because there is mutual interest either way. So that's how we dealt with it. So we are out of time. I just wanted to have one more deck summarizing the reference architecture, right? The different tools, and then I'll hand it to Frank to go into the details. But the bottom line is that as data scientists, you need a set of tools to build models, do exploratory analysis, and do a lot of batch processing offline, right? So your selected platform should support that capability. So often in our team, we make extensive use of Jupyter notebooks on the front end. It's mostly for exploratory data analysis. There is also Apache Zeppelin for those of you who are Zeppelin fans. But all the heavy lifting, which is building the models and all of that, is pushed to a backend environment, which could be a data lake. So in our case, we have an enterprise data warehouse called Greenplum. We also have a Hadoop native SQL engine called Hawk. And all the modeling toolkits that we use here have capabilities for building large-scale machine learning algorithms. The prominent workhorse for our analysis is MATLAB. Frank will again talk to you in more detail. But we also harness a lot of libraries from the Python and R ecosystem to build these models at scale, right? So now let's say you've built these models. Now you want to be able to communicate insights from the model. Now for that, you have to apply these models on incoming data, right? So you have your connected car, it's sending all the sensory information. You want to do some sort of pre-processing before you can apply a model to score incoming data, right? So for that, we use Spring Cloud Dataflow. It's got a lot of good features. It supports a multitude of sources and a multitude of sinks. You can attach any sort of processor module to it. It's all based on Java, so it's easier to maintain. A lot of developers already use the Spring framework. We use Apache Geode, which is an open source in-memory database. The commercial version is called Gemfire, and it helps in a lot of transactional processing. So if you have hundreds of thousands of vehicles, millions of vehicles, you have sensor data coming from all of these vehicles, you need to be able to cache that information to understand, okay, what vehicles on the field are experiencing a certain predictive maintenance issue. You want to expose that to dealers in the form of an application. All of those smarts and power and speed is built into Geode, which is why it is also part of this reference architecture. And the end user, in this case, it could be a dealer, it could be an automobile manufacturer, they get to see an application where we use the trained model to essentially say, okay, how many vehicles on the field, on the road, are experiencing a certain maintenance issue? The dealer might be interested in calling these vehicles for a routine checkup. The auto manufacturer would want to know if this is just restricted to certain vehicles. They want to basically do anything that they have to do to avoid a NHTSA-issued recall. So this architecture, we'll dive a little more deeper into it, and you can reserve your questions after Frank is also done.